Okay, calculus, now that we've gotten through the first half of chapter 2, where most of what we've been doing has involved estimating or approximating a couple of different ways of getting rates of change or limits, we're finally now moving into what you guys probably remember from last year in pre-calc as the quote-unquote real way to evaluate limits. And the number one method that we're going to be using to doing this here is going to be the factoring and canceling method. Essentially, we kind of flirted with this idea a little bit back in section 2.2. What tends to happen is that in 99% of the limit problems that we are asked to evaluate, we're trying to take the limit as x approaches a certain value in its domain, which we normally would call a, and in this example we're going to do in just a second, that a value is 3. And what almost always happens is that when you try to do direct substitution, when you try to plug that a value into the function itself, not surprisingly, we end up with a problem. Most notably, a discontinuity in the function of one of the three types we discussed in 2.4, either a point discontinuity, a jump discontinuity, or an infinite discontinuity. And when that happens, everybody, we usually need a different method to figure out the value of the limit itself. And this example that we're going to work right now would be a perfect example of what I was just talking about. Even though it doesn't often work, the first thing that you guys want to think about, the first method that you want to try when it comes time to evaluating a limit is that direct substitution method, or what we would call plug and chug. But you should not be surprised when this happens. Here, I think this is going to make trouble for us. If we go in the numerator here, we've got a 9 plus a 9, which is 18, minus 18 is a 0. But more important, down in the denominator, 3 squared minus 9 is going to get us a 0 as well. And that 0 over 0 means that the function here is not defined for x equals 3. Therefore, the concept of direct substitution does not work at all. So what we're going to try to do instead is find a function that is functionally equivalent to this particular rational function we were given. And of course, the way we're going to do that is by factoring and canceling. So I'm going to try to be thorough in the way that I write this out, but if you guys want to take some shortcuts to save a little bit of time in terms of the amount of writing that you do, I think that's okay. Up in the numerator, it sure looks like we've got a quadratic trinomial that's going to factor here. That x squared is going to break up into x and x. I read my signs now, and the fact that c is negative tells me that these two signs are different. One's a plus and one's a minus. And I need two constants now that multiply to negative 18 and combine to a positive 3. So that is going to be a, let's see, a negative 3 and a positive 6. It's how that numerator then is going to factor. Down in the denominator, hopefully we recognize this one right away as a difference of squares. That factors into the product of two conjugate binomials, an x plus 3 and an x minus 3. And now that we have factored both the numerator and the denominator, the first thing we want to look for, and of course you see it already, is the identical factor of x minus 3. Now guys, I want to be very, very clear. You are looking at it completely the wrong way if I see you guys do this and then this. We can't cancel these things out term by term, but the entire binomial factor of x minus 3 is what cancels with its identical factor on the other side. Now, to take you back a ways, what we have just found, everybody, is a whole, or a point discontinuity. When you've got an identical factor on both the top and the bottom, we know here that we have a whole that exists at, actually not as an ordered pair, let me just go ahead and write it out. The value of x that would make this factor become 0 is 3. So I know that whatever we're left with, which is actually going to be this rational function right here, x plus 6 over x plus 3, that function has a whole that exists at x equals 3. However, for our purposes right now, we're just interested in knowing what the limit of this function is as x approaches 3. And now, with this problematic factor of x minus 3 eliminated, now we can simply plug the 3 directly in here, and we'll come up with our answer very quickly. In the numerator, that's going to be a 3 plus 6. Really, I should have an equals here and an equals here as well. Should be a 3 plus 6 on top and a 3 plus 3 on the bottom, which is going to get us an answer here of 9 over... Oh, guys, we're not going to see this anywhere, are we, for an answer of 2? I certainly hope not. Anyway, that's going to give us a 9 on the top and a 6 on the bottom. We'll divide out that 3, and we'll end up with 3 over 2 for the limit as x approaches 3 of this particular function right here. Okay? If we wanted to see what was going on in a little bit greater detail, we could graph that function there. What I would expect to find, everybody, is that this function itself, I guess I could do this pretty quickly by hand, the function that we're graphing, which is actually this original function here, looks exactly like this simpler version of the function right here, x plus 6 over x plus 3. We have a vertical asymptote at -3. The degree of the numerator and the degree of the denominator are the same. They're both 1, and the quotient of their leading coefficients, 1 over 1, is 1. So we've got a horizontal asymptote now at the line y equals 1. And the only other thing I really need to worry about is what quadrant this thing exists in. So really quickly, if I were to put in, let's say, 0 for x, I'd end up with a 6 on top, a 3 on the bottom. That would be a 2. So I get the ordered pair 0, 2. And that one point right there tells me that this hyperbola exists in the upper right-hand quadrant formed by its two asymptotes. So it's going to do something like this, but before I go to draw the rest of it, I want to remember this fact right over here, that this graph has a hole, a point discontinuity right there at x equals 3. So as I go to graph it, I should probably stop there, make the open dot, and then keep graphing the rest of it looking like that. And I'm pretty darn confident that if this hyperbola existed in the upper right-hand quadrant, it probably also exists in the lower left-hand quadrant, but it's not a bad idea to put in a number to the left of your vertical asymptote, like maybe -3. That would get me a, -4. That would get me a 2 on the top and a -1 on the bottom. 2 over -1 is -2, so yeah, that gives me a point right there, and now I feel pretty good about saying that the graph looks something like this. Okay, so with that hole involved right over there on that side, you'll notice, everybody, that horizontal asymptote right here was at y equals 1. This was the point right here where y was equal to 2. That hole should have a y coordinate somewhere between 1 and 2, and guess what? That limit that we just came up with is the y coordinate of that hole. So we actually could be more specific right now and say that the hole here exists at the ordered pair of 3, and then that limit value of 3 over 2. That would be a more specific way of giving the exact location of a point discontinuity or of a hole. Okay? Regardless, I spent a lot of time working on that. None of what I did here in terms of the graph is really necessary. Basically, factoring and canceling is going to get you the limit in a very efficient manner. I thought I would give you a difficult problem like this just because I don't think you guys have seen a problem like this in a while, and it really scares people when they see it at first. So, unlike the last problem that we just did, that numerator is not very easy to factor just by looking at it and thinking hard. It's a cubic 4-term polynomial, everybody, and that is not something that you have spent very much time at all in your lives factoring. So I'm going to walk you through how to do this without cheating and looking at the calculator here, guys. It's a limit as x approaches 7 of... And here's the hint. Start with the easy part. The denominator of this fraction, x squared minus 5x minus 14, is a quadratic trinomial. So that should be pretty easy to factor. Let's try it. The x squared becomes x and x. The signs now, again, a minus right there for c tells me that one is a plus and one is a minus. And I need two numbers now that multiply to -14 and combine to -5. That's going to be a -7 and a +2. So that's the only way that that denominator factors. Now, what everybody needs to understand, two important things. Number one, you can't just plug, and I should have talked about this earlier, you can't just plug 7 in here. 7 squared is 49, minus 35 is 14, minus another 14, not surprisingly, gets you 0. But of course, that's easier to see right here. If you plug that 7 into the x minus 7, your second factor, you're going to end up with 0 there. And of course, whatever you multiply that 0 by is going to get you 0 as well down in the denominator. Okay? All right, so we've got the denominator factored. But what everybody needs to realize is, and I want you guys to think like a math teacher for just a second, okay? There would be absolutely no point to giving you guys a problem like this if one of those factors in the denominator wasn't also a factor of the numerator. And furthermore, I don't want to make an assumption, although that's clearly what I'm doing, but I am going to verify that assumption. The problematic factor down in the denominator is this one right here, which is x minus 7. The only way this problem is interesting at all is if x minus 7 also happens to be a factor of the numerator. Now let me be clear, you guys, and I hope you're listening and not just watching. I don't know that that x minus 7 belongs there. It's a hunch, but we're going to verify that in just a second. And this is going to take you back to a skill that you guys learned over the last couple of years. If you think you know one of the factors of a polynomial, we can do synthetic division, everybody, to try to figure out if x minus 7 is in fact one of your factors, and if so, what the quotient would be when you divide it out. So I'm going to skip a little bit of space right here, but not too much. If you guys remember this, the 0 or the root of x minus 7 is 7. We write that first, that goes in the box. After that come all the coefficients in your polynomial in order from the highest degree to least. So we start with a 1, then a negative 4 for the x squared, then a negative 26, and then a plus 35. All right. After that, we skip a line and then draw a line. We begin by bringing the 1 straight down, and now we multiply. The 7 times that 1 gets us 7, and we write that number right here underneath the negative 4. Now we add going down. The negative 4 plus 7 gets us 3. We do the same process again. The 7 in the box gets multiplied by that 3 to make 21, and we write that underneath the negative 26. Let's add those two. Negative 26 plus 21 is negative 5. We multiply the 7 in the box times the negative 5 to get negative 35 here. We add those two up, and as dumb luck would have it, we end up with a remainder of 0. And the fact that that remainder of 0 tells us that our hunch was correct, that x minus 7 is in fact a factor of the original cubic 4-term polynomial there. And not only that, because the remainder is 0, but these three numbers right here are the coefficients of what our quotient is, what we call our depressed polynomial. We began, everybody, with an x cubed. Now it goes down a level, and this one is the coefficient of your x squared term. So we've got 1, 3, and negative 5. That's going to be an x squared plus 3x minus 5. So that's a trick that you guys talked a lot about over the last couple of years. You may have forgotten about, so I wanted to walk you through it. It's not going to show up much, so don't panic about that. Okay, with where we are right now, we have factored both the numerator and the denominator, and the problematic factor of x minus 7 does in fact cancel out from both the numerator and the denominator. And what normally happens now is we're now left with a resulting function that is continuous, let me finish my sentence, that is continuous at x equals 7. This thing looks like it has an infinite discontinuity still at x equals -2, but I don't care what happens when x is -2. I care what happens as x approaches 7. So in the numerator, everybody, the 7 squared is going to be a 49 plus a 21. Looks like it's going to get a 70. 70 minus 5, last I checked, was 65. And down in the denominator, the 7 plus 2 is going to get us a 9. And last I checked, everybody, 65 and 9 don't have any common factors, and that's our answer there. So that was a little bit ugly, everybody. Again, I don't want to scare you. I don't think you're going to be getting many problems like this at all, but I'm pretty sure there are 1 or 2 that show up on the homework from this section, and I didn't want you guys to panic too much when you got there. Okay, so that was example B, and that's really all I was going to do with you guys for factoring and canceling. Hopefully you guys remember how to factor. Let me go ahead and show you guys one little shortcut right here, and I'm not sure if you guys know that your calculator does this or not. Although I did ask you to play with this just a little bit on that calculator worksheet that I gave you guys after we finished chapter 1. One of the things that the Inspire CAS will do that the non-CAS would not, okay, we need to remember, guys, these calculators understand algebraic symbols and manipulation, and so they, come on, here we go, they will do some of this work for you. If I were to hit menu and add a calculator, and then go to menu, what we're asking our calculator to do now is factor for us. That's an algebra skill. So if I type in number 3, and then number 2, we can go ahead and type in a polynomial expression. That polynomial we had in that problem was x to the 3rd power, and that's as much as I remember now. Let me go back. Minus 4x squared minus 26 plus 35. Okay, so it was minus 4x squared minus 26x. Is that what it was? Yep, and then a plus 35. Unlike the solve feature, guys, you don't have to tell it what variable to use now. There's only one variable, and it'll factor that for you into the x minus 7 times. Hey, and sure enough, x squared plus 3x minus 5. So good to know that we got that one right. Okay, back to this one now. A second method we're going to talk about is called trigonometric simplification. All right, and in this particular mess right here, let's see what's going on. It's a limit as x is approaching pi over 2 of the quotient of tangent of x divided by secant of x. And again, the first thing you ought to try on every single limit problem is direct substitution or plug and chug. But again, it shouldn't surprise you when this doesn't work out well. Tangent of pi over 2, everybody. Well, as I'm hoping you remember, pi over 2 is the location of the first asymptote of the tangent graph. What that means is that tangent is undefined at pi over 2, so right now you've got problems. I don't really care what the denominator is. The fact that your numerator is undefined means I'm not really going to get an answer to this problem. Although furthermore, if we were to try to take the secant at pi over 2, well, let's think about that for just a second. Secant is the reciprocal of cosine, and cosine is your y-coordinate. At pi over 2, which is straight up at 12 o'clock, your y-coordinate or your cosine is 1. I take that back. I'm sorry. We're talking about your x-coordinate right there. Oh, that didn't sound right to me when I said it. So secant is the reciprocal of cosine. Cosine is your x-coordinate. Let's try that again, Mr. Fontana. And at pi over 2, your x-coordinate is 0, which means that its reciprocal is going to be undefined as well. So when you get undefined over undefined, that's obviously a problem. Well, one of the things that we can do, this does not fall under the umbrella of factoring and canceling, but we can try to rewrite an expression with trigonometric simplification that might suit our purposes just a little bit better. So if you guys think back to all of those problems you've done over the last 2 years where they gave you a trig expression and asked you to try to simplify it, well, this is where that might come in handy. For example, one of the tricks you guys were taught years and years ago is that tangent can always be rewritten in terms of sine and cosine, and tangent of x is actually the sine of x divided by the cosine of x. Furthermore, down on the bottom, secant of x can be rewritten as 1 over the cosine of x. So with that in mind, we now have a complex fraction here, everybody. We're now taking a fraction divided by another fraction. So we could rewrite this as the limit as x approaches pi over 2 of, and here we go, my numerator fraction is sine of x over cosine of x. And rather than dividing by a fraction, I'm going to multiply that by the reciprocal of that fraction, cosine of x over 1. And now what you probably see already is that the cosine of x on the bottom and the cosine of x on top cancel each other out completely. So where are we now? Well, not in a bad spot whatsoever. This is now the limit as x approaches pi over 2 of just plain sine of x. Don't need to put that 1 down there on the bottom at all. And the great thing about sine, everybody, is that it is a function that is continuous for all real numbers. Sine of x, like cosine, has no holes, no jumps, and no asymptotes, which means to evaluate this limit, this is a continuous function, we can simply evaluate now the sine of pi over 2, our y-coordinate there, which is 1. Now, I want to make very clear something that I'm a little worried somebody might have thought a second ago. A couple of minutes ago, I wrote that this was undefined over undefined. And I want you guys to realize that the answer to this question is 1. I do not want anybody to think that you knew the answer was 1 because anytime you divide something by itself, you always end up with 1. That statement that I just made isn't true. To make it true, what we'd have to say is when you divide any number, any real number, other than 0 by itself, you do end up with 1. But it doesn't work for dividing 0 by itself, and it especially doesn't work when we're talking about undefined quantities. You can't divide something undefined by itself because it simply does not exist. So let's not fall into that trap, everybody, of thinking that undefined over undefined is automatically going to give us 1, although that did happen to be the answer to this problem. Okay, so that was a little trig simplification there. Conjugates are another idea within section 2.5. And this actually does relate a little bit to what we did earlier with the factoring and the canceling. But unless I opened my big fat mouth and said that, which I just did, I would ask you guys if you thought there was anything that we could do to clean this up in terms of factoring. And most people are going to look at the x minus 4 down on the bottom and say, nope, that binomial is prime. You can't do anything with it. And on a pure sense, you guys are right about that. So one of the methods that we use sometimes, especially when you're dealing with radicals within your binomial, is to multiply both sides of the fraction, the top and the bottom, by the conjugate of one of those two pieces. And if you guys have forgotten this, the conjugate of a binomial has the same first term, but the opposite second term. So I'm going to take the conjugate of this expression right here that has the radical in it. And its conjugate would have the same first term, the square root of x, but the opposite second term. Instead of a minus 2, that's now going to be a plus 2. And of course, I can't multiply the top of a fraction by something unless I multiply the bottom of that fraction by the exact same thing right there. Okay, so that is one thought, although as I look at that, yeah, I think this is going to work out for us. So that we can do. What I'm essentially doing is kind of putting a big bracket around all of this. And let's see what that does for us, if anything. Maybe I'm wrong. So this is now the limit as x approaches 4 of, and up in the numerator, interesting things are going to happen. Let's go ahead and let's do FOIL here, guys. First product, the square root of x times the square root of x just gets us x. What shouldn't surprise you is what happens next. When we go to do outer product, which is the square root of x times 2, that's a plus 2 root x, and the inner product, which is a negative 2 times the square root of x, that was a plus 2 root x minus 2 root x, those two terms are going to cancel each other out completely. This happens, you guys, every time we multiply two conjugate binomials together. The outer and the inner products are opposites of one another, and they wipe each other out completely. So now we just need to worry about, we did first, outer and inner are gone, the last product, negative 2 times positive 2, that's a minus 4. Now down on the bottom, we could do FOIL with the x minus 4 times the square root of x plus 2, but that would be missing the point. If you take a look at our numerator now, guys, we're in really good shape. I'm going to leave the denominator factored, x minus 4 times the square root of x plus 2. And now what I'm hoping you guys recognize is that we have an identical binomial factor of x minus 4 on both the top and the bottom. And that factor, you guys, which was right here, that's the one that would have been the problem if we tried direct substitution. So now that the problematic factor has been eliminated, now we can go ahead and let x actually become 4. So the numerator, when everything cancels, is just going to be a 1, and in the denominator, that's now going to be the square root of 4 plus 2. Last I checked, the square root of 4 is 2, and 2 plus 2 is 4, and that's our answer there, everybody. 1/4 is the limit for this problem right here. So by multiplying both the top and the bottom by the conjugate of the numerator, we got that problematic factor of x minus 4 to cancel out completely, and then plug and chug became something that was available to us. That works. Let me talk for just a second, though. Do I have time? Yeah, let me go ahead with this because I think it's fun to talk about. Take a look at the original expression we were dealing with, guys. The square root of x minus 2 over x minus 4. Square root of x minus 2 over x minus 4. And when I asked a while ago, does that factor, okay, most of you guys probably looked at that and said no, because you can't do anything with the x minus 4. Well, I see your point, but let me give you a similar problem down below that. Let me go with something like, how about n minus, let's go n minus 5. And underneath that, how about an n squared minus 25? Now, if I asked you guys if this one factors at all, let's see what happens. You can't do a thing with n minus 5, so it stays the same. But we have a difference of squares on the bottom of n plus 5 and minus 5. The n minus 5s in their entirety cancel out, leaving us then with a 1 on the top and an n plus 5 on the bottom. And that's all you can do to simplify that expression. Now, the reason that one worked is because the denominator, n squared minus 25, is a difference of squares. And you guys have spent a lot of time really going all the way back to Algebra 1 4 years ago, factoring a difference of squares. If I asked you guys to go back up to this example on the top, and if I asked you, is x minus 4 a difference of squares, you would all probably look at that and say no. And what if I said, make it work? What if I said it could be looked at as a difference of squares? Let's see if we can do what I call force factoring. So if you ask yourself, how did you get n here and here when you factored? The answer is because n is the square root of this term right here. How did you get 5 and 5? It's because 5 is the square root of that term. Well, we're going to do the exact same thing here, guys, down on the bottom of this fraction up here above. Take this number right here, which is x, and take the square root of it. The square root of n squared was just n, but the square root of x can't be simplified. It's just the square root of x. Now, you got 5 by taking the square root of 25. So take the square root of 4 here, and you're going to get a 2 here and a 2 here. And anytime you factor a difference of squares, one term is positive and one term is negative. I'm not going to take the time to do it, but if you were to do FOIL here, well, I guess I am. First product, square root of x times square root of x, that's x. The outer product here is minus 2 root x. the inner product is going to be plus 2 root x. And the last product here is going to be a minus 4. Well, sure enough, these two terms in the middle cancel out, leaving you with the x minus 4 that we were looking to factor in the first place. So that's what I call force factoring, everybody. You're kind of shoving a square peg into a round hole there. And if you had noticed that, then the numerator stays as the square root of x minus 2. And now all of a sudden, you guys, that binomial cancels with that binomial and leaves you with 1 over the square root of x plus 2, which is exactly what we ended up getting way back over here, right here basically, when there was a 1 there, and there it was in the bottom. So that's a way to kind of circumvent the whole conjugate thing right there. All right, I'm going to try to wrap this up pretty quickly. Another one with conjugates, this one's a little bit more complicated, and your author kind of liked this type of problem. You'll notice in the last example we did, you guys, I multiplied the top and the bottom of this fraction by the conjugate of the numerator. Here, we're going to do it a little bit differently. It's the denominator in this fraction that has the radical in there, and that's what we're going to multiply by the conjugate of. Now let me say the words out loud again. A conjugate binomial has the same first term but opposite second terms. So if I look at the blue denominator here, the same first term would still be the square root of h plus 4. But now instead of a minus 3 at the end, there's going to be a plus 3 at the end. And of course, we will do the exact same thing in the numerator, square root of h plus 4 and a plus 3. And again, what we've really done is put brackets around all of this. Okay, so where are we, guys? It's now a limit as h approaches 5 of, the numerator is the ugly part right now. I am not going to waste my time trying to simplify that, so I'm going to leave it as h minus 5 times the square root of h plus 4 plus 3. But down in the denominator, let's work on FOIL here. We have binomial times binomial, so here we go. First product, the square root of h plus 4 times the square root of h plus 4 is just going to be h plus 4. The outer product here, from here to here, is going to get us a plus 3 times the square root of h plus 4. The inner product will be the exact opposite of that, minus 3 times the square root of h plus 4. So once again, when you multiply two conjugates, the outer and the inner products wipe each other out. And all we have left to consider is the last product, negative 3 times 3, which is a minus 9. And if you look at that real quick, you'll recognize that that denominator is going to simplify into h minus 5. Well, sure enough, the h minus 5 on top and the h minus 5, which is what that really is, on the bottom, cancel each other out completely. So we are now taking the limit as h approaches 5 of just the square root of h plus 4 plus 3. Our denominator is just 1. So that becomes the square root of 5 plus 4 and a plus 3 at the end of all that. 5 plus 4 is 9, its square root is 3, and 3 plus 3 is going to get us 6 for the answer to that limit problem. All right, that's a fun one right there. I enjoy that. And then this is the last example I have for you guys here today. I just called this miscellaneous and random because I didn't quite know what to call it. I'd never seen a problem like this before this particular textbook right here, but your author thought it was interesting and threw a couple in there, so I gave you an example. We've got two different fractions right now, and they're being subtracted. Obviously, if you tried to plug a 7 in here, you get a 0 on the bottom, and of course the same thing is going to happen right here. So plug and chug crashes and burns as a method here pretty darn quickly. But let's see what we can do with it, guys. This is going to be equal to the limit as x approaches 7 of, well, what we're going to try to do is get a common denominator among these two terms. And I'm hoping you guys see already that the x squared minus 49 is an x plus 7 times an x minus 7. This fraction on the left already has an x minus 7, so it's just missing an x plus 7 factor that we'll put on both the top and the bottom of that first fraction. So the numerator now of the first fraction becomes x plus 7 minus the numerator of the second fraction, which is 14. And our common denominator here, in either order you want, is x plus 7 times x minus 7. Now, right now, plug and chug still gives you the same problem of a 0 in the denominator. But if you take a look at your numerator, a little bit of simplification is going to make everything work out nicely here. The numerator, x plus 7 minus 14, is really the same as x minus 7. So that x minus 7 cancels with that x minus 7, leaving you with a 1 over x plus 7. And now, sure enough, letting x actually become 7 works out just fine, and we end up with 1/14 for our answer to that limit problem. All right, guys, so that is a wrap on 2.5. So when the directions say to actually evaluate a limit, not approximate it, not come up with an estimate, but to actually find a limit, these are the methods we're going to be using in section 2.5. Good luck, everybody.